Hi, kids. All right, we're gonna talk about Unit 2, which was dynamics. Hopefully, this will be a very dynamic talk about dynamics. Lots of people just call this Newton's laws. So, this is Newton's three laws. So, let's start with Newton's first law. I'm going to say NFL, but Newton's first law. So Newton's first law. Newton's first law just states that, hey, you know what? If you add all the forces up and you get nothing, then your A is nothing. And this is, hey, you know what? That an object at rest stays at rest, an object in motion stays in motion along a straight line. As long as you add all the forces up and you get nothing, your acceleration can be zero. This is lots and lots of problems you will see where they talk about, hey, you have a constant velocity. Well, anytime you see that, you should be immediately thinking, oh, that means my net force is zero because my acceleration is zero. So Newton's first law with that. Remember, this also relates to inertia. Inertia is the tendency for an object to keep its state of motion. Remember, inertia relates to mass. More mass, more inertia. So, more inertia, more mass, less acceleration for the same force. All right, so that was Newton's first law. Newton's second law is just that, hey, you know what? If you add the forces up and you don't get zero, then you will accelerate. In fact, the rate of the acceleration depends on the net force and it depends on the mass. So we often write F net equals ma, or the sum of the forces equals ma. On your equation sheet, it is written like this. To tell you for a couple reasons. One, the direction of the acceleration depends on the net force, and really it's the net force doesn't really depend on this. The net force depends on adding all your masses or adding all your forces up and seeing what you get. The acceleration depends on this, and it depends on your inertia. So, maybe you might see a graph that looks something like this, net force and mass, and hey, you know what? Your slope will be your acceleration, something along those lines. So, all right. Newton's second law was most of this unit. This is our problems where, hey, maybe you are, I don't know, you have this random box sitting here and you are going to push it like this, and the box is going to end up moving this way. So then you'd have to draw all the forces. Well, you have this applied force. You have this normal force. You have the force of friction, maybe. Maybe there's friction acting on it. And then maybe there would be this force of gravity going down. And why did I draw it so small? Because if you draw in your components, this plus this would have to equal this. And if it's accelerating to the right, then my forward force would be bigger than your backward force. So again, what do you do in physics class? You draw a picture. And in this case, you'd have to draw two FBDs, one for all the parallel stuff, one for all the perpendicular stuff. And then you write your equation and solve stuff. We did lots of problems with inclines, so hopefully you are okay with doing that. But, if I was to sketch this in, maybe you have a force like this, a force like that. Maybe our box is moving up the incline, so that means that there's some friction pointing this way, and if we break this into its components, you would get something that looks like this. So where this is my normal force, this is the force of gravity, this is the force of friction, and my angle goes right here. So this would be Fg cosine theta, and then this would be Fg sine theta. Okay. But we've done lots of problems like that. Maybe there's going to be a problem where, hey, you're riding on an elevator. So we have this, hey, there's somebody in an elevator. let's say that it's moving this way, but maybe you draw your FPD and you get an FPD that looks like this, FG, and then your normal force. Well, geez, this would mean that I'm accelerating downward. So if I'm moving up and accelerating down, I'm slowing down. But remember, this Fn is the normal force. Okay. Sometimes it's also called apparent weight. Why? Because it's, in this case, you would feel lighter because so your, apparent weight would seem like it's less. Um, just make sure that you understand the normal force. For example, here, the normal force is equal to this. The normal force here is equal to this plus this. So lots of people just assume the normal force is equal to the force of gravity, and it is sometimes, but it's definitely not all the time. So don't memorize, understand, and apply. We did some stuff with force of friction. So if you remember, we did a lab where you graphed this, and then the slope was mu, which was our coefficient of friction, which just tells you how sticky the two surfaces are. If you look on the equation sheet, you would see where it says this. And you might ask, well, why does it say that? Well, actually, it says this. Okay, there's a less than or equal to there. So first of all, this is going to be a lovely equation to help you find the magnitude, not such a lovely equation to find the direction. Draw your FBD to find the direction. Second, the reason that there's less than or equal to, if it is mu k, which is kinetic, then it's equal to. Why? Because that's how big the friction is. If it is mu s, which stands for static, okay, that's where it could be less than or equal to. If I have, let's say, this random battery and I push on it just a little bit, well, you know what? Static friction is holding it in place. But the static friction is probably not equal to mu times the normal force. It's going to be, in this case, less than. And I could keep pushing if I push harder and harder and harder. And eventually it's going to get going where then now it goes from being static friction to kinetic friction. But the reason that there's a less than here is that static friction is only as big as it has to be. Okay. Let's see. Then we talked about Newton's third law. So let's do that. Newton's third law, which in essence, for every action force, there's an equal and opposite reaction force. Sometimes it's written like this, where force that 1 exerts on 2 is equal to the force that 2 exerts on 1, but it points the opposite way. The negative sign would be points the other way. Another way of saying this is that forces always come in pairs. I like to say it's Newton's third law, not Newton's third sometimes, which means, hey, it is always true that if you have two forces, and then those two forces have to be the same. It's always object 1 exerts on object 2, then object 2 exerts on object 1. And you might think that this is super easy and super basic, but it's so not. This will explain how something, for example, if you have a rocket ship, there's my beautiful picture. But if I was to draw my forces, the forces on the rocket ship would be the force from the gas going this way. And then you would have the force of gravity, and if my rocket ship's going to accelerate upwards, that's what it would look like. Well, the action-reaction pair here would be the rocket pushes the gas backwards, the gas pushes the rocket forward. Okay? You'd have that. You could talk about somebody walking. If I have my person here walking along, that if this person is going to walk, how do they walk? Well, the way that they walk is they have to push backwards on the ground, and then by Newton's third law, the ground pushes them forward. Same thing with the tug of war. If you wanted to win a tug of war, how do you win? You can't pull harder on the other person than they're pulling on you, because it's not Newton's third sometimes. It's Newton's third law. So how do you win a tug of war? Well, then you have to push harder on something else. You have to push harder on the ground than the other person is pushing. So, Newton's third law, for every action, there's an equal and opposite reaction force. Please, please, please don't get those questions wrong. And then Newton's third law problems, we had our basic Atwood problem, where it was something like this. Okay, as long as this pulley is close to massless and frictionless, then this tension and this tension here would have to be the same, because that would be my Newton's third law pair. Chances are you will probably see a problem like this, where you have this type of deal, but again, where you got your Newton's third law pair. Maybe you would see a question like this, where it's on an incline, so, but if you need practice on doing those problems, please practice doing those problems and being able to set it up. But in essence, it's really just you draw an FBD. Maybe there's no friction, so that's what my FBD looks like. FN, FG. You draw a different FBD. This would be FT, where this FT and this FT have to be the same size. That's my Newton's third law pair. And then this FG, maybe I'll call it FG2, and I'll call this FG1. This FG would have to be bigger because it's going to accelerate down. But those type of things. So hopefully that helps. And that was Unit 2 really fast. Bye, kids.